to you by Johns Hopkins University. And we do still need volunteers for lecture note takers. For this lecture, we would like to volunteer for that. No. We got one.
Okay. We didn't do one for Ibou, but
yeah,
that's good for now.
Great. Okay. Yeah, so our first speaker this morning is Ibou Bah, and this is his first lecture on Lagrangian methods for categorical symmetries.
So I think I'm the first proper physicist talking in this meeting.
Well, I don't know about
that. So just for you, David, I'll be extra physicsy today. Okay, so on that note, I should try to maybe just, since the enterprise that we all hear is to figure out how math and physics can talk to each other in a way that's productive, it's important to sort of, at least from my perspective, what is the difference between the two types of people? So mathematicians like to know what they're talking about. They like definitions, axioms, and so on. And physicists, to first order, we just like to mess around and find out what happens. Okay, and this is our technical job title. We go out in the world and we throw things at each other, see what happens, and make measurements and try to figure out what you can learn. And of course, in that note, when we do theoretical physics, we do theoretical physics in the same spirit. We do mathematics in the same spirit. We just like to assume we know what we're talking about and work with it until something fails. If it fails, we move on. If it doesn't fail, then we try to ask what you can learn. So these lectures are going to be in that same spirit. We're going to sort of mess around and see what we can learn. So the main topic is what is QFT. That's what we're trying to understand very broadly. I don't have an answer for that. I don't know how to define a QFT. But in physics, by now, we have a good sense of that if you have a QFT, what should it do? Okay? So I'll try to explain that part. What do we expect the QFT to do, to behave like at its most basic level, and how you can sort of formulate it. So today, I will try to just say something of try to address the QFT in general, what it's supposed to do. And in the next lecture, I will try to start to discuss finite symmetry groups here. And in particular, the things that we will try to understand is constructing the topological operators associated with them. And then some of the things we would like to understand is how it acts on field theory. In this case, the canonical model we will try to use as an example is SUN Yang-Mills theory. If we succeed, hopefully towards the end, I will try to also describe constructing general topological operators with Lagrangians. And how you might compute fusion rules and how you would play with it. And all of these ideas, of course, is going to try to use one picture that we know that all physicists know how to play with QFT, which is use Lagrangian. And how we should, that's our main tool. Okay. So I encourage everyone to just jump in, ask questions, say what you want. I'm not going to be offended, I promise. But be as engaging as possible. It will make it much more fun. And also as the lecture goes, there are 4 lectures, and depending what people want me to discuss more, please, by all means, let me know, and I'll try to adapt accordingly. Okay. Okay, so let's go to the first topic. So what is a QFT? I don't know what a QFT is. I would like to understand what a QFT is, but there is something else you can do better, which is that if you you go off the street, you ask a physicist, what do you want a QFT to do to you? The following thing is the thing that you want to do. So first, if I have a QFT, what I should expect is I have a list of operators. So these are operators which I can consider working in some manifold, a compact Lorentzian or whatnot, or Euclidean. I have some operators O with some label I that I insert in some position in space-time. Okay. You can also have another set of operators. So these are the things that we call local operators. They're inserted at specific points in space. You can also have extended operators, which are inserted on some p-dimensional extended manifold in space-time. Okay. So first, I would like to have a list of operators. And then there is another thing that I want. 2, you want to have some Hilbert space of states. So how should we think about this Hilbert space of states? Is if we consider the space where we're defining our quantum field theory, which is something like R, which is a time direction that you pick, find some spatial slice, Y. So this is not good book work. Yeah. You might consider this space as having some boundary that we can take this T going to infinity here, right? So at T equal to infinity, I would like to define a set of states, which with some label psi, let me use something else, A, which I define at infinity. And typically in a quantum field theory, you have some evolution operator, which we will call something like the Hamiltonian, which evolves you forward in time. Okay. So I want to have a list of operators. I want to have some Hilbert space of states. And these operators can act on these states in a linear way. And then finally, I need some machine, which I will generically call the partition function. Okay, so what does the partition function do for me? The partition function, what it does, is a machine that gives me correlation functions. So it will take some set of operators, OI, OJ. You can insert extended operators if you wish, and then it will spit out a number, which is generically in C. So the least, whatever a quantum field theory is, it has to be able to do this, right? I have to be able to give you a list of operators which I would typically call observables. I have some Hilbert space, which are what I would call states. There is an evolution operator, which is what we call the Hamiltonian, and then we have a partition function, which basically has a way of taking these operators or these states and spitting out numbers. And those numbers are the things that we wish to observe. So notice that I have made 0 attempt of defining anything here. And it fits very well with how we do physics. Okay. So what is an operator? A physicist would say, I know when I see one. Okay. And when we talk about operators, it sort of asks the question of what are the things that I can measure, right? So an operator or a field, an operator could be associated, for example, the electromagnetic field here, right? That's an operator, the field, and it's an operator that we like to measure in some particular way. Okay, so giving you this list, there are some basic principles they must satisfy. Any quantum field theory have to satisfy there are three sort of principles that we associate with. One is unitarity. Two, we have locality. And then three, we have causality. Okay. So given this list, they must satisfy some principles, or more precisely, these correlation functions that I compute. The correlation functions that I compute have some constraints on them that are imposed by having a unitary quantum field theory, a local quantum field theory, and one that is causal. And all of these three things, of course, you can give 10, 20 lectures and barely really scratch what they're supposed to mean and what they're supposed to do. So I'll try to give a lightning review of some aspects of it. Questions? Okay, good. So first, unitarity. In two lines, unitarity is, in quantum mechanics, it's the principle of conservation of probability, or preservation of probability, if you wish. It's better. Okay, there's various ways to understand this notion. In the most basic sense, as I said here, in a QFT, I give you this list and I want to look at these correlation functions. In the real world, what these correlation functions give us allow us to compute one observable that we care a lot about in the world, which is the S matrix, for example, in the standard quantum field theory. And what the S matrix is that I have some asymptotic region over here. This could be T going to minus infinity, and I send in a bunch of particle states, and they do something happens, and then at a later time, T going to infinity, I measure some new particles. You know, the number doesn't have to be conserved, which is an important thing in quantum field theory. And there's a map that goes from here to here, which is what we call the S matrix. Okay, it's a linear operator that maps the Hilbert space of particles there to the Hilbert space of particles here. And unitarity from this point of view is S dagger 1. Right? So this is a famous conservation of probability. So any quantum field theory must satisfy this condition. But of course, not all quantum field theory admit an S matrix. That's an important fact. Conformal field theories don't have S matrix. QFT that we care about don't have F matrix, right? So, but there is a more basic way to understand unitarity from the point of view of the correlation functions themselves. And this is a statement that usually goes under reflection positivity.
Sorry, can I ask a question? When you're talking about the S matrix, do you have these operators applied?
Good.
Or this is without the operators. I would have thought the operators would change the probabilities.
Very good. So in the QFT, I have operators that I've defined, but I haven't told you how to define a particle state. So from the sort of intuition you would have, operators, they create an excitation, which is what the typical thing that I would call a particle state. or they create an excitation in the field, in the quantum field, which I haven't said anything about, and that's what we would call the particle state. And in quantum field theory, the way we usually do this is that at infinity, there's no interactions. We just have free particles in both sides. Any interaction that happens is somewhere in the middle, right? And those interactions are going to be constrained by these principles, right? And unitarity is the statement that the S matrix is the unitary operator itself. It's a map from the Hilbert space at minus infinity to the Hilbert space at plus infinity.
Is that right, that you could put a defect at negative infinity and?
We haven't talked about defects yet.
Okay.
We'll maybe later.
Oh, sure.
So the picture here is exactly the typical picture you might expect what a physicist does in the lab. There's an apparatus, there's an experiment, you throw a bunch of stuff at it, they bounce back, and then you see. This is exactly that. Right? And then try to learn something about what's happened inside. Okay, so reflection positivity is a way of sort of understanding unitarity from the point of view of the general correlation function. So to see this, we briefly look at in quantum mechanics. In quantum mechanics, where we have finite dimensional Hilbert space, if you have some state, so in mechanics, you can have some state psi, which evolves under a Hamiltonian to phi of t. You can also have an operator O, which is so this is in the Schrodinger picture. In the Heisenberg picture, we can define an operator O of x at some initial time 0, which can act on a state and then evolve forward. You can either evolve the state or you can evolve the operator to OX of t of psi. Okay. So unitarity from this point of view is a statement that the norm of the state, where you have an observable, is positive. Okay. So, and typically we write this by saying phi O dagger O phi is a positive thing. When these are observables, and this is a good state in the Hilbert space, it could be 0 if you have null states, for example. But there's nothing that prevents you from doing that. So from the point of view of a quantum field theory, the statement that we would say for this is, if you consider the correlation function so I have to have a notion of what I mean by this daggering. In quantum field theory, if you take an operator in Lagrangian space, you can extend this to a complex time, t plus I tau here. The daggering from this perspective, OX t plus I tau dagger, you identify with the reversal along the imaginary axis of time. Right. So reflection positivity here is a statement that if I look at the correlation function of O at x plus t minus I tau of x, t plus I tau, this quantity is positive. And if I fully do a Wick rotation, imaginary time, reflection positivity is simply the statement that O of x at I minus I tau is this correlation function of O of x at I tau is positive. And of course, I can have as many operators as I want. So I can consider OI x at minus I tau, Oj x minus I tau with some number of them, and then the reflection of this Oj x of I tau Oi. So this whole quantity must be positive, and this is a condition on the list of these operators that has to be satisfied to maintain unitarity. Go ahead.
So just to be clear, you're saying that we can extend time to the entire complex plane, not just the other one?
Yeah, so we can talk about so in quantum field theory we can consider extending time to if we pick t equal to 0 where we define the state, then this is upper half. Sorry. So we extending over the full complex plane. So I'm considering t as being what I'm starting here. So we're extending it to the full complex plane along the imaginary axis.
And the fact that unitarity is the same as or implies reflection positivity, this is just for CFTs or in general?
No, not for CFTs, for field theory. We want to impose reflection positivity. Because any field theory should be unitary. And this is one way. So if I work in Euclidean space, this is how I can implement unitarity.
I thought it was kind of just in the CFT, the reflection positivity and unitarity was the same.
It's a condition, it's a minimal condition that I need to have unitarity in the field. Any more questions? Okay, so the other condition that I want to impose is locality. Locality is one of those things where if I have one way we get to know when a QFT is local, which I'll talk about later, is when we write a Lagrangian, right? So at the level of the OPE, at the level of the operator, you can ask, how do I impose locality? So intuitively, locality means that when I have any interactions here, they create excitations at the same place where the interactions occur. Okay. One way to sort of formulate this statement is to think about the OPE. So in general, the OPE in a QFT is something wild, and we can discuss a lot about it. An OPE in a CFT is precisely defined, and it exists. So the statement of locality, you can formulate it as an OPE statement that says that if I have an operator OX, OJ, and I bring sitting at X1, sitting at X2, and I bring them close to each other and ask how this acts, this should act as a sum, some coefficient Cij, in the limit where I bring X1 and X2 close to each other, if I consider this insertion, times some operators that I insert, let's say at X1. So this is saying that the action of these two operators is going to look the same as an action of a single operator that I put at one of them. And the sum, these are coefficients that depend on space-time variables. They could be singular in various ways, and the singularity will reflect short distance physics associated to the quantum field theory. Okay. In a general QFT, this is at best an asymptotic series. In a CFT, this is something that is well defined, and we understand how it is. But this is one way to sort of implement locality in a quantum field theory, to say that if I bring two insertions close together, what should they do? They shouldn't create an excitation far away. If they create an excitation, it would be here.
Can you expect something for extended operators too? Like I can bring a local to an extended and they go.
Yeah, so if we have extended operators, things should happen in a region where they come together. We can talk about OPE of extended operator.
Would that be local or global?
Would that?
In if I have topological operators, it's of course ultra local. The question is if I have two Wilson lines and I bring them close to each other, what should happen? If they create a state, it would be a state at the location where they come together. And of course, in those cases, you could ask that if I have two particles and I bring they're interacting via what we call a force law and so on, but we know we're not supposed to think about it that way. We're supposed to think about the fact that there's a mediating particle that are exchanged. If I have extended operators, there's still some mediating thing.
One more question. So you just made a statement that said an extended operator creates a state.
Sorry,
How do I understand
I was being very colloquial in the
No, there
physics
must be a
sense.
meaning to that. Like, what is the?
If I have two extended operators, they come together, they just create another operator here. If I take two operators, and I bring them together, the action of those two operators, I should think of another operator that I insert here.
So what's, is that a local operator?
No, it's not gonna be a local operator.
So it won't create a state.
I said, forget that.
I'm just trying
Forget the shape. That was an answer to hit.
Is it right that the sense in which it's local when you bring two extended operators is that you have an expansion in the tangential directions to their
In a sense that if I have U of gamma, right? One U of some gamma two, if I bring them together, it's what I'm putting them is on top of gamma one, gamma two. This should be something that depends on just one of the gammas times some other coefficient. That is in that sense what I mean. No, forget that I said the word state or anything.
There is the option of taking the tubular neighborhood of the extended operator to create a state. So, I mean, there's a confusion that you could in potential think of a state that lives in the boundary of a tubular neighborhood of the extended.
Yeah, but that is a way of trying to describe an extended operator, which is independent from the fact of bringing them together. That's a different thing.
I'm just trying to parse the difference.
That's right. That's a different. I mean, if I have any insertion of an operator, I can always carve out a tubular neighborhood and try to define a state that lives there. Right. That's saying that that's one of the ways I can think about an extended operator. I can even think about a local operator in that way, right? So if I try to define a local operator formally, what I should do, I mean, what does it mean to insert something here? What I should do is I carve out a small spherical neighborhood and then give you some data on that. Right? That's how I should define a local operator and then take the limit at this small. In the same sense, if I have an extended operator, I carve out a tubular neighborhood and give you some data there and then take the limit. That's the statement that you want. That's a general thing that we should do carefully always in talking about operators. That's independent from the fact that when I bring them together. So when you bring two, what you want to do, you want to carve out a tubular neighborhood that includes both, and then associate some data around that. And that should define for you a new set of operators, and that could be a sum of things or whatnot. Thank you for those questions. Okay, so one way we can think about locality is from this point of view of an OPE, that if I take two operators together, I can think of it as decomposing it into a sum of some other local insertions. And then the last bit is causality. So this was locality here. And the last bit, which we need to impose, is causality. And very broadly, causality is a statement that operators that are space-like separated commute. Okay, that's the general statement of causality. And any QFT must satisfy these conditions. And from these conditions, you can start to derive other properties that they must include.
And you say where they commute or how they commute? How do they commute or where do they commute?
Okay, good. So let me try to put a little bit more meat on this. So in general, locality and causality are different notions. They feel like they're similar, but they're different. If I have a Lagrangian quantum field theory, and this is the case that will work, they're different, but they're related. Right? And one way you can sort of make the statement that they're different but related is when in the Lorentzian quantum field theory, when you have you can think about the statement of causality that said that if let's say you consider the light cone sitting in Lorentzian space, and you insert an operator here, and then you insert some other operator there which are in the same light cone of each other. Causality means that you can go to a frame, to a reference frame, where these two operator insertions are at the same point, but different points in time. This is one way to think about causality, that there exists a reference frame that if two operators are in the same light cone, that you can go a frame where they're sitting at the same point, but different time. Okay, and then locality, this statement here, the way to think about it is to say that if you have two operators that are inserted outside each other's light cone, then you can find a reference frame where these two things are happening at the same time, where you have a reference frame where you insert it here, where you're inserting them at the same time location. So these are events that are simultaneous. There's a reference frame where these events are simultaneous. So from this point of view, this is what we mean that they commute, right? So this excitation here, because it's over here, it will not affect what's up. That's another way to say it in a Lorentzian picture. Go ahead.
How do you define space-like integration and QFTs?
Well, a QFT is evaluated in a fixed background, so you have a metric. As opposed to gravity, which is not evaluated, where you have necessarily a fixed background.
Depend on the QFT.
Hmm?
The statement you look to me like a geometry statement. And like, how can I have something which looks like a QFT which doesn't satisfy this? But I can have things which are non. This looks to me more like a geometry statement than a field.
I'm not sure that so these insertions are specifically in positions, right? I can take these positions, the statement about the commutator is saying that O inserted at x1 and O inserted at x2, where x1 and x2 are space-like separated. You can imagine at short distances writing each one of these as some sort of OPE. It's a statement that if I look at the difference of two OPEs, they're vanished. So you have the statement of this kind, right? It's not automatic that whereas if these points are not space-like separated, right? There's no reason to assume that this should vanish. You can see that this is a non-trivial condition on the statement, on something like that. All right, so these are the sort of the three broad principles that any QFT must satisfy. So one thing you might want to do is, in trying to construct a quantum field theory, any way you can construct a quantum field theory, meaning you have a machine or algorithm that allows you to generate a list of operators of various kinds. And this includes a notion of a partition function that gives you correlation functions, and the correlation functions satisfy these conditions. I would call this a QFT.
Yes, you can tell me to shut up. The causality, the way you explained it makes sense for point local operators. It feels like it could be more subtle for extended
Yes,
operator.
it is.
I mean, you could have somehow two operators where
I did not attempt to talk to define it for you.
that a thing. People
I don't know how to talk about it sharply, so I will not try right now. And the way that I can talk about that in a way that is sharp, at least from my perspective, is writing down a Lagrangian, right? Which we'll get to. Oh, okay. So before I just proceed with these statements, so you have this list. There's certain nice properties that comes in along when I'm talking about a quantum field theory, which is that there are a couple of more statements that one could make in addition to these things. Some of them you can prove assuming Lagrangian symmetry. Actually, you can prove it assuming Lagrangian symmetry, which is that quantum field theories will, so I'll write 4 with a star, technically not an independent thing. You have a cluster decomposition. So what does the cluster decomposition means? It means that if I consider some correlation function, let's say I set like OI, x1, inserted at x1, OI, OJ at x2. And then I have another set of operators that I insert at O1 plus some coefficient B, OJ, with a different label, let's say I prime, J prime plus B. If I consider something like this, and I take the limit as B goes to infinity, right? So this is a picture that I have a set of operators that I insert around here. Then I have another set of operators that I insert around here, and I take the limit as I push them apart, that this thing should factorize. It should factorize into O1, X2, as the correlation function should factorize. So if I insert operators here and here, and I push this to infinity, and I look at that correlation function, it should factorize. This is a cluster decomposition. And then we also have renormalization. Or more precisely, that you have some UV QFT, like, and then you have some IR. If I have a QFT, there's the UV and an IR. So UV and IR here, we're saying that high energy modes. Low energy modes. This it also is usually also thought about as saying the short distance physics. And the long distance physics. That these two things, vectors, decouple. Okay, so this statement that the quantum field theory have this nice property that the UV the high energy modes and the low energy mode decouple, or the short distance physics and the long distance physics don't talk to each other, or they talk to each other in a way that it gets summarized with very few finite set of numbers in the low energy physics. Okay, so wait, does this notion of high energy short distance and long distance make sense to people?
I understand that in some way, like if we have this decoupling, we get this cluster like the two things lead to each other in the way that like reflection positivity and
yeah, they're related, In a sense that, so the cluster decomposition is about insertion that I do in space. And the UV IR decoupling is what I go to the momentum space and actually say that things also decompose. Okay, they're related in that sense. Go ahead.
It's like causality and cluster decomposition quite related in terms of like if you have causality, like if they can
Yes. So as I said, these are not independent things. They depend on those, right? So in fact, in quantum field theory, these are statements that typically want to prove. But in axiomatic QFT, usually these are axioms that you put in trying to get far. That's why I'm putting them as a separate thing. And also the reason why it's worth discussing, like these statements seem rather trivial and obvious that this is what that I want these things to be true about QFT in the world, but gravity fails to satisfy both of these conditions. Gravity is not local, right? So neither of these conditions are true for gravity, for gravitation, for quantum gravity, whatever it's supposed to be. Okay, so that's an important fact. We have gravity in the real world. Gravity is not a quantum field theory, right? And it doesn't satisfy these conditions. Okay.
Does it's not satisfied just for a 5 or also
Neither. Gravity doesn't have cluster decomposition or UV-IR coupling.
but it's still local, right? Oh, shit.
And this is I mean, it's the both of these facts, the way that we see it is that you know, in the low energy we have gravity, and the low energy gravitational theories have black holes. Black holes are extended things. They're large. They're fat. Black holes break cluster decomposition, and black holes also, the states that make up a black hole are UV states. They're high energy states, but we see them in the IR, so they affect the IR in a non-trivial way. So they don't also satisfy this UV and IR decoupling. Right? That's one. There's many other interesting ways to see this phenomena, even at a perturbative level, about gravity. But the sort of thing that you should always think about, the things that gravity have that quantum field theories don't, are black holes, and black holes create a lot of problems for you.
What about unitarity?
Good. So gravity has to be unitary, right? Because if it is a quantum, unitarity is a statement of quantum mechanics, right? So we, you know, we can be comfortable giving up locality, right? I mean, in fact, even we can write non-local quantum field theories. We can think about non-local quantum field theories. That's fine. But unitarity is a statement of quantum mechanics, right? It's a deep statement, so we can't give that up. And the question that you're asking is that indeed, when I add black holes, they seem to violate unitarity, but we know that has to be fixed in some way. And there's a lot of work going to there. I mean, I can give a whole nother talk about it, but gravity has to be a unitary theory. Go ahead.
So you said we are okay giving up locality. I mean, it's a property we can compromise on.
Yes.
But I mean, this whole collaboration is based on.
I haven't had the symmetry yet. Good. So okay. So these are the principles that for QFT that are immutable. We must have. The principle implies something like this. So the example of gravity is just a counter example. Why you need to spell these things out. Then comes now the sort of nitty gritty of the matter, which is that if you know. So here I haven't made an attempt to say anything of what these labels mean. Right? What do these labels mean? This is where our collaboration comes in. Right? So there are all of these amazing properties of QFT. Each one of these you can spend years and years studying and what they mean, and from very general principles. But the thing that we're studying in this collaboration is actually what these labels mean. Right. So in a typical quantum field theory, these labels are associated to representations of some symmetry that's acting on the Hilbert space of states. Okay. And when I'm computing correlation functions, the answer that I get on this side depends on what I mean by these labels. And that's what we mean by the symmetry action. Okay. So, beyond just sort of telling you what this list is, the sort of workhorse of characterizing these correlation functions is symmetry. It's symmetry. These will satisfy word identities of various kinds, and those control the properties of quantum field theory. And of course, now when we talk about, thanks for the question. So the main objective of our collaboration is actually understand kinematics of operators in quantum field theory. Right. That is the goal of the collaboration. What do these labels mean, and how keeping track of those labels constrain the answers of these correlation functions? And this is the study of symmetries. Okay. So I like to do this because I like to remind you that the world of quantum field theory is giant and completely uncontrolled, and we're just trying to understand one corner, what the labels mean. Questions? Okay, good. So with that said, now you could ask any sort of construction that you have that gives you a list of operators, that has a way of giving you states, that has a way of giving you partition functions, is a model of a quantum field theory. And so far in physics, there are a few ways we can do this. And I will highlight a couple. The most rigorous way that we have of defining a quantum field theory is the lattice. So what the lattice does is that it sort of discretizes space in some way, right? So we have space is gridded in some particular way, and then you have points. You have finite number of points and finite number of sites, and you can associate degrees of freedom at each one of those finite number of points and finite number of sites. Okay, and then when you do that, then at each point, a finite number of points, finite number of sites, you have a finite dimensional quantum mechanics living there. So the whole system is finite, and you can rigorously define a quantum mechanics on a lattice, and then you can compute things with that. And then you can take the limit where the lattice spacing goes to 0 to some continuum. Okay. So this perspective highlights one of the things that makes quantum field theory very hard. Okay. So when we consider these insertions that we have here of these, for example, the local operator at every point, what this is telling you that at every point in space, you have some quantum system living there. And then you have an infinite number of points in a given space. So you have an infinite dimensional system at hand. This is the thing that makes quantum field theory hard. This is one of the things that makes quantum field theory hard. And this is one of the reasons why when you try to compute anything in quantum field theory, you get infinities from which you have to regulate in various ways. Okay. So because of this, when you start on the lattice, you can define quantum mechanics associated to the lattice, which will give you some finite dimensional Hilbert space. You can construct operators explicitly, depending on the degrees of freedom that you associate at each one of these points. And then you can take the continuum limit to try to define a quantum field theory. Okay. This is the most rigorous way of talking about QFT, at least from a physics point of view. The other ways that we've been able to sort of get out of the list of something like this is what we broadly call geometric engineering. So ironically, this is a way of obtaining quantum field theory that sort of uses a much heavier enterprise, which is string theory. So string theory is a picture where it's where we have a perturbative definition of a string theory that we can study, and from them we can derive actual spacetimes. So if you take a string theory and then you decouple gravity, then you can define QFTs, quantum field theories, with actual geometric objects. Okay, so for some of the experts in the room, this is like, for example, the world of class S physics. Class S constructions of quantum field theory, where different QFTs are being given to you by some Riemann surface and insertions on a Riemann surface from which you can use to compute correlation functions. Okay, so this is another world which basically we've studied, we can use to define a QFT. And lastly, the one that is the subject and also the oldest, most canonical way is Lagrangian. Okay, and this is the one that I will want to talk about for the rest of this. Any questions? There are other ways you can try to, right? But the thing that I would like to remind you is that there is really nothing sacred about each one of these things. Each one of these things are ways to get out of the quantum field theory. So, for example, geometric engineering can make something else obvious, which the other models cannot. One of the things that often happens is that when we think about this partition function that computes this correlation function, it will depend non-trivially on choices of parameters of your system. So you have a family of quantum field theories with some parameters associated with them. You can also have background fields for which the partition function or the quantum field theory depends on. So all of this gives you a family of quantum field theories, right? And those family of quantum field theories, they will be given by some geometric object. This sort of approach makes that obvious and straightforward. The lattice map model, what it makes obvious that you can have what it makes obvious is that you should be able to always renormalize quantum field theories in a sharp sense, right? It makes this picture come out more. And then Lagrangians, which is what we will talk about, what it makes explicit is the locality properties of quantum field theories. Right? It makes quantum field theories local, and locality is going to be built in from the beginning. Right? And there are other ways you can try, and if you can come up with a creative way of getting at this list and having those properties satisfied, you also would have invented a new way to talk about quantum field theory, which is completely legitimate. Okay, so we move on to Lagrangians. Any questions?
I have a very big one. What does decoupling